All right. So for today's seminar, we will have the presentation from Ellen first, and I will share like the some like the topics as the next like the presentation. Yeah. Thanks for sharing.
So I'll try to share the key ideas of this paper, which is trying to study the invariant metrics and symmetrized by disk through the Bergman metric, and we'll see exactly what those means. Okay. So we have already covered what are the invariant metrics. Uh, Before invariant metrics, the metrics invariant under biholomorphisms. The Kobayashi-Ryan metric and uh, complete Taylor-Einstein metric and character metric. It's also character-Riefan metric. Um, I'll not get into the definitions of these metrics, which I've already covered in the earlier seminars. And also, we have seen in the case of, for example, uh, Poincare metric on the disk, all the four metrics coincide with the Poincare metric. And right now, we are interested in this object, symmetrized by disk, which is denoted by the name G2. Into that one, or from D. And uh, this symmetrized by disk, we can also look at it as a um, uh, image of a map phi, phi from D cross D to C2, where G2 containing C2, where Z1 comma Z2 goes to Z1 plus Z2. So, in general, we are interested in studying the equivalence or comparisons of these invariant metrics on a complex manifold. In particular, right now, we are interested in this symmetrized by disk. We wanted to study their equivalence or comparison and how they're related and so on. So, in order to do it, how do we start the comparison? Like we are going to use a result of Wu and Yao. And let me share the paper. It's this paper, Wu and Yao. So there are, let's try to understand the result here. This is a result on about invariant metrics on negatively pinched complete Kähler manifolds. So the negatively pinchedness part is what we are going to use, and we'll see what exactly is happening here. Suppose if we take a complete Kähler manifold with m comma omega, and if we try see whether the holomorphic sectional curvature is negatively pinched between two negative numbers where a and b are positive, so minus a holomorphic sectional curvature is negatively pinched between minus b and minus a. Then we have comparison between the Kobayashi-Radon metric and the Bergman metric, and we have exactly the equivalence level comparisons on both sides. Similarly, we also have other result with the Taylor-Einstein metric. If we have the negative pinchedness of the holomorphic sectional curvature, and then we have comparison of the Taylor-Einstein metric with the Beckman metric. So, in some sense, if we are able to tell the holomorphic sectional curvature with respect to the Beckman metric is negatively pinched and also bounded below, it's not just negatively pinched but also bounded below from below. Then we'll be able to show that the uh, uh, Bergman metric is equivalent to Kähler-Einstein and also equivalent to the Kobayashi-Radin metric. So, with this two results in hand, our interest in studying the equivalence of metric has now reduced to just studying the negatively pinchedness and boundedness. In the sense, we wanted to understand, let's just see, holomorphic sectional curvature. That has now reduced to studying the holomorphic sectional curvature, whether they're bounded below and they're bounded above, and if bounded above, whether they're negatively pinched. You have to study all of that. So now, holomorphic sectional curvature, we have a vector field. HFX is nothing but where R is the Riemann curvature. X. Now we have to do the calculations in order to calculate this. Uh, in order to study the behavior of uh, homomorphic sectional curvature, we have to obtain the some explicit expressions and see whether we can tell something about it. In order to do it, like we have uh, two ingredients or two ideas before we start with the calculations. For example, let me tell the two helpful ideas. The first is our goal is to calculate this holomorphic sectional curvature explicitly and see
Ellen,
whether we can.
Ellen,
Yeah. Yes.
what is
Yes.
HFX? HFX is a holomorphic sectional curvature, right?
Exactly. Exactly.
But the formula is something different that what you written, right? So R of x comma x bar comma x comma x bar divided by mod x power 4, right?
Right. Um, right.
So it's
So
quotiented by norm of x power 4, right?
uh, just confirm it. Mhm.
It's the unit vector condition, so the denominator
Yes, yes.
Right. We will see that we'll do something about this norm later eventually, where we don't have to worry about it. And now, in order to do these calculations, we try to see use two ideas. The first is this, that is, now we have the uh, uh, map phi from P cross D to G2. And the map is expressed as z1 comma z2 going to z1 plus z2 comma z1 times z2. Now, the point to note is like this map is not 1, 1. For example, uh, you can just like switch it like 1 comma 2 and 2 comma 1 both goes to the same. So in the sense it is like 2 to 1 map except in the diagonal, where in the sense like if it takes z1 comma z1, then there is no 2 to 1. So the point is like it's like a 2 to 1 map. If it's a bijective, then we can look for its whether it's biholomorphism and other things. But the point to look for is like this is a proper holomorphic map. So we can try to uh, uh, take the Bergman metric on the domain D cross D and try to push forward and handle the expressions in G2. So before we do that, the Bergman kernel expression on D cross D is easy to obtain because the Bergman kernel and Bergman the Bergman metric expression is easy to obtain because like if we take two uh, uh, there are results like if we know the Bergman metric on expression on M and N, then the product is in terms of Bergman metric, it will be the product of the same of B M cross M says B M times B. So now it's just reduced to knowing the Bergman metric expressions on uh, that unit disk. And we earlier saw that the Bergman on the unit disk Bergman metric and all other four invariant metrics coincides with the Poincare metric. So using that, we'll be able to tell the it's like 1 by 2 by square.
Yeah, Josephine has a question.
Yeah. So this condition the Bergman of M cross N equals Bergman of N M and Bergman of N. So is it true irrespective of choice of M and N, right? True in general.
I have to check the state like a reference to see what conditions are there, but probably Gunhi can have the points.
Okay, I see.
So what's the exact question?
So is it true like that condition, I mean, irrespective of the choice of M and N, like are there any conditions on M and N such that equality holds, or it's true in general?
This is I think let me think. So this is my way of thinking. So Bergman corner is coming from the Hilbert space of the L2 holomorphic functions basically, and the corner is extracted from the orthonormal basis of such like the Hilbert space. So for M cross N, so we have all L2 functions on the holomorphic maps. And so this equality, I think, is like should be interpreted in a way that so the projection with respect to first and the second component behave nicely. So if that's not the case for some of the like the complex manifold, then this equality might fail. But many classes, because the projection itself is just the reason that's a nice like holomorphic function, so it just behaves nicely. That's what I have.
Oh, fine, fine. Okay.
Yeah, I
Thank
think this is already very long. You can simply just check.
Okay, okay. Yeah, thank you. Yeah. Please go ahead. Thank you.
So uh, so we have the Bergman kernel expression on D cross D. Now we can try to push forward whenever phi is not degenerate in the sense like the Jacobian for phi is invertible. And we can do this as a small exercise. You can calculate the Jacobian of derivative of phi and at what points they're not invertible. So now, for example, when we do have to do the metric components for the uh, Bergman metric on G2, when we have to take the derivatives, we can use the chain rule and try to like use this expression on D cross D and try to calculate. I'll show explicitly how it's done. And so this is one helpful idea where the explicit expression, we are just using the expression of the Bergman kernel on D cross D to get expressions on the G2 on the symmetrized by disk. The second idea is like, now we have to check the holomorphic sectional curvature to be negatively pinched and bounded below on each point of G2. However, if we try to know, since we are dealing with the Bergman metric, which is invariant under automorphisms, that is biholomorphisms, if you know the automorphism of G2, then we will be able to reduce the set of points on which at which we have to calculate the holomorphic sectional curvature. For example, if we try to, let me first write down the automorphism group for G2. Now, suppose H is an automorphism on G of G2, then what happens is H is an automorphism. Then there exists let me just phi belonging to automorphism of D. That's the H of let's say phi of Z1 comma Z2 is equal to phi of phi of Z1. Now, the point to note here is the automorphism group on D is like homogeneous in the sense like it's transitive. It can switch any 2 points. It can take any point to any point. So using that, what we can actually do is like we can make this point go to 0. We can make one of the points go to 0. And let's say that we are making this point to go to 0, the second point to be psi of Z2 to be equal to 0. And psi of Z1, we don't know where it is, but what we can actually do is like after making Z2 go to 0, we can apply rotation, which is still an automorphism, where the 0 point is fixed. But the Z1 is like psi of Z1, wherever it is rotated enough to bring it back to the positive real axis. So after it is brought to 0, psi of Z1 can be rotated to be brought to belong to this line, 0. So what happens is the given any 2 points in the it's written as corollary 3 in the paper, which is like given any W1, W2 belonging to G2. Now I'll just fix some notation. Whenever I write Z1, Z2, they belong to the disks. And whenever I write to W1, W2, they belong to the symmetrized by disk. So now W1, W2, since phi, the map that we have is surjective, there will exist some Z1 and Z2 such that W1, W2 can be written as psi of Z1, Z2, psi of Z1, Z2. Now we can pick an automorphism H such that like this Z2 is brought to 0, and then it's rotated enough such that this belongs to 0, 1. So in the sense, there exists H in automorphism of G2, such that H of W1, W2 is equal to x, 0, where x belongs to close 0, 1. Okay. So what happens is like in order now we have to verify the negatively pinched plus bounded from below of the holomorphic sectional curvature, not on every point of W1 and W2, but just on the points x comma 0. So it's just like real dimension is 1 now. If you see earlier, W1 is a complex number, W2 is a complex number, so the real dimension is like 4. So the number of variables that you have to deal with is like reduced from 4 to 1, which is like really huge when we go to the calculations. Okay, so now I'll just give a pause for a moment. So what we have done is like we have just reduced the studying the equivalence of metric to uh, uh, to understanding the holomorphic sectional curvature behavior on on the symmetrized byte in order to calculate the holomorphic sectional curvature, that is in order to calculate the Riemann curvature tensor, and we are trying to get some explicit expressions. And the first thing is like we use the Bergman kernel expression on D cross D. So, and using the push forward, we can get the Bergman kernel expression on G2, and the derivatives metric tensor, and so on. And the second point is like instead of verifying on the whole, in terms of dimensions, like a 4 real dimensional object, we have reduced that. We have to verify the whatever the holomorphic sectional curvatures behavior on a single line on one dimension. So these two in hand, like now I just want to go ahead and tell like what are the calculations that are done. So I can try to show one at a time. And before doing that, I can show what are the things that are involved and then show the paper. So the like in order to calculate the holomorphic sectional curvature, this one starts with metric tensor, then the inverse metric tensor, then Christoffel symbols, then the curvature components for the vector fields like dou I. And I'll quickly write down what dou I means before we proceed for some notational things. Dou I will actually mean dou by dou Wi. I is equal to 1 and 2. And this W1, W2 are basically coordinates on G2. And since it's you can think of it as local covers, like where in the sense like W1 and W2 can be written as images of Z1 and Z2. The W1 is Z1 plus Z2. Let me write it below. W1 can be written as Z1 plus Z2. W2 can be written as Z1 times Z2 with Z1 comma Z2 being in this. And whenever there is Z2, like partial derivative with respect to Z2, we'll write it as dou by dou Z2 explicit. Okay. So now coming back and showing this, there is metric tensor to be calculated, an inverse metric tensor, Christoffel symbols, and curvature components for the vector fields, like with respect to the vector fields, dou I as the basis. And we'll try to do this Gram-Schmidt articulation for the vector fields with respect to the Bergman metric G. And the where it eventually comes and helps is exactly this point. In the denominator, if we choose our vector field to be unit vector field, then this is taken care of. This part, this norm of x power 4 is taken care of. So we do that process, and then we do some explicit calculations of holomorphic sectional curvature, bisectional curvatures at these normalized vector fields, and we make some observations there. Then we go on and finally calculate the holomorphic sectional curvature at any unit vector field. And finally, we conclude that at any unit vector field, axis C will be negatively bounded below and also negatively pinched. Okay, so let me try to take you through the paper. And so 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 we start with this. The derivative, the B is going to stand for the Bergman kernel on D cross D. And before we start to do anything with the Bergman kernel on G2, we try to take all the derivatives first up to fourth order, which will be eventually required in all the calculations. So this proportion 4 basically covers the explicit derivatives of the Bergman kernel B at the coordinate x comma 0. And those expressions are like calculated. These calculations can be done using Mathematica. We can write codes to do these calculations in Mathematica, and can also verify, but it will take a lot of time. The whole calculations will take a lot of time. And the next point is like the once we have these derivatives, now we can proceed to calculating the Bergman metric and Bergman metric on G2. And if you actually see, this is like we actually see here it is. So the BG2 can be locally written as B composite phi inverse. And in order to differentiate them with respect to WI, just to recollect, W1 is equal to Z1 plus Z2, and W2 is equal to Z1 times Z2. So, and when we make this change of variable from Z1, Z2 to W1, W2, and this is exactly the chain rule that we apply. And this dou Z1 by dou WI bar, dou Z2 by dou WI bar. I'm not sure whether they're calculated. Yeah, they're already written here explicitly over here. And we just use all of these expressions that we've already calculated and try to compute the first derivative and eventually the second derivative, dou ij bar of BG2. And this leads us to the metric components. Dou ij bar of the metric of the metric expression BG2 will give us, we have the metric components for the Bergman metric, and these are the expressions. And with this in hand, it's immediate to like we can calculate the components of the inverse metric components of the Bergman metric. And again, it just requires us to calculate the determinant and then take the inverse. And these are the expressions. And now the Christoffel symbols. And until now, we will be required to use only the up to second order partial derivatives of the Bergman kernel of D cross D. And from in the Christoffel symbols, we'll have to do up to until the third order. And the expressions are explicitly given. I am not sure how to talk about the again the same idea of using the chain rules again. And these calculations are like I've tried to verify them. I was trying to do these calculations using Mathematica. Probably if there is time, I'll try to show those calculations. And once that is done, then we do the curvature components for the Bergman metric. And again, like here we'll use up to fourth order. Just the reason why we have calculated up to order 4 for the derivative of Bergman kernel on B cross D. Okay, so these are complicated further expressions where the fourth derivative of the Bergman kernel on G2 is like broken down and split into the products of different derivatives on the Bergman kernel on okay, here it is. So yeah, so the fourth order derivatives are broken down into the fourth order, different order derivatives of the Bergman kernel on D cross D, multiply with derivative of Zi by W case. And so basically this is just to highlight, this is a nice expression that this fourth order derivative of Bergman kernel on G2 is now just explicitly written in terms of the derivative of Bergman kernel on D cross D, which is just B, times the derivative of that comes arise out of the change of variable. Okay, so now until this point, what we have got is like we have got the Bergman, we have got the curvature component expressions with respect to like the vector fields W1, W2, where this is nothing but dou by dou W1 and dou by dou W2. And if you remember the expression that we have got, let me try to compare. The metric components is over here. Exactly. So we have some metric expressions. We want to see whether these are, with respect to this Beckman metric, we want to see whether these vector fields are at least whether normal to start with. So what happens is they're not. So we'll just start with, for example, if we write it as G1, G2, G3, G11, G12, G21, G22, and we can consider this dou1 as the basis. So feel like it's like dou1, 0, it's like 1. Like then we'll get like the with respect to this metric, we'll get G11 as the output. So if you want to normalize it, you want to write it as divided by the square root of it, G11 bar. 1 bar. And so this is like, this we call it by the name X. So this is like when we choose the first vector in a basis V1 by norm of V, that's the same thing that we're doing here. And let's call it by X. And there is one more vector field to handle. That's exactly, you take the vector V2, which is dou2, divided by root of G2 command, to G22 bar, and then minus with inner product of this, whatever the vector that you have, with the first vector that you have, X, and multiply that constant with that. That gives us again more complicated expressions. A1 is this, A2 is this. If you remember, all this G1, G2 are like fractional polynomials, and just trying to recollect, they're all like fractional polynomials, like polynomial by a polynomial, and this Y eventually, like we just write it here this way, and just to point out. Mm, Even I can point out with this proportion here. Now we have two unit vector fields, two vector fields X and Y, such that like G of X comma X is equal to G of Y comma Y is equal to 1. That's their norm is 1. And then G of X comma Y is 0. We'll see later, but the point here to now notice, like, let's try to calculate H of the holomorphic sectional curvature at these two vector fields alone. They are anyway unit vector fields right now. If we try to calculate that, then what we get is H of X is this complicated expression, and H of Y is like even more complicated over here. But the point to note down that I want to highlight here is we have reduced like 4 real variable to 1 real variable. And if you try to handle the whole calculation with the four variables, this will be extremely clumsy to calculate. That idea that we actually used in the beginning, the automorphism, using the automorphism group and reducing the set to a one-dimensional set is actually very helpful. And that's something that I would like to stress. So in particular, after doing these calculations, what you can observe is like the H of X and H of Y are negative on the interval 0, 1. And not just that, even as limit extends to 1, you will have, even at that point, you will have the holomorphic sectional curvatures to be -1. So, which basically means they're negatively pinched. Now, but we want to check at all the unit vector fields. Before we proceed to calculating H of V for any unit vector field, we do the bisectional observation of the bisectional curvature behavior. So with just these two unit vector fields X and Y, we are going to calculate B of X comma Y. And that turns out to be there is the observation here is b of x comma y at this point 0.9 comma 0.9 and 0 comma 0. This turns out to be positive value. In the sense, holomorphic sectional curvature is negatively pinched, but the bisectional curvature obtains a positive value at some point in the domain. So uh, so basically that is not negatively pinched. That's observation here. So before we proceed to seeing the holomorphic sectional curvature on any unit vector field, this is the bisectional curvature is not necessarily negatively pinched. And the observation, the proof of the main theorem is here. That idea is like you take any unit vector field as like a times x plus b times y. It's just 2 dimension. So where modulus of a square plus modulus of b square is 1, norm is 1. So this becomes a unit vector field. And for r of v comma v, using a multilinearity and other things, like we try to write it explicitly in terms of r of different combinations of x and y, and which exactly turns out to calculating these expressions that are required, which are given in this lemma. So it boils down to knowing the h of x expression, holomorphic sectional curvature at x, at y, and bisectional curvature, and 3 more combinations, and they are exactly obtained in this lemma 13. So if we, after doing this expression, and like the Kunhi, Cho, and Leon, they are able to observe that the that it is negatively pinched, the holomorphic sectional curvature. In fact, they take another expression, 3 minus 2x square, the whole square, times the h of v. And this is positive, and it stays away from 0 for x in 0, comma 1. So for this expression, they're able to show that L of v lies between minus 10 and half. So which basically essentially means h of v should be negatively pinched and bounded below. So now trying to, after this long calculation and other thing, the main observation is this, that holomorphic sectional curvature is negatively pinched and bounded from below. And that leads us to the initial question that we started with. Using the theorem from Wu and Yao, we are able to see, it's mentioned in this corollary. That's the Bergman metric, the Kobayashi-Redden metric, and the complete Keller-Einstein metric with Ricci curvature equal to -1, and the symmetrized by this G2 are uniformly equivalent. And this can exactly be proved using the theorem that we saw. So with theorem 1, which actually showed that the holomorphic sectional curvature is negatively pinched and bounded below. And the corollary follows from the theorem 2 and 3, which I showed at the beginning of this session. And using those 2 theorems, these 3 metric are proved to be equal. And with that, there are some more significance that I wanted to highlight. But I'll just stop here. And,
Yeah, thank you very much for
and
that
see if you have any
summary.
questions. Yeah.
I'm actually happy to see like that. So someone cares about like the previous lecture result. So any like the questions or comments?
Yeah, I'll wait for their questions. After that, I'll just share 2 more significance that I feel, and then stop. I'll wait for.
I have a basic question. So what is the biholomorphic group of the symmetrized bodies?
So it's exactly the atom of some group of D. I think so. Let's see. Here is the proportion to, which talks about automorphism of G2. So what it says is like any automorphism, if you take of G2, that can be written as there exists an automorphism in D, and it can be written as like h of those points can be written as phi of this. So I see. So um, I'm not sure whether we can conclude that automorphism group of G2, I don't think it can be done. It's not isomorphic to automorphism group of D. Can we conclude that, like, from this proportion? Um, mm,
I guess so, in a sense that so if you have an automorphism H in G2, then we can find the Möbius transform and vice versa. So just correspondence.
I was just worried, like, this phi is not surjective or bijective. So will that cause an issue? But I don't think so. Right. So this map basically Hutch going to this Hutch. We can try to show that this is an isomorphism. And so basically the automorphism group of G2 turns out will become automorphism group of D. And one more thing is like, yeah, I'll stop here. And if you have any questions further on this, after that I'll add some more.
Sure. Thank you.
Okay. So the other point that I just came to me, which I thought I'll share, is like similar to symmetrized bidisk, we can construct symmetrized polydisk. For example, G3, there can be elements of the form Z1 plus Z2 plus Z3, Z1, Z2 plus Z2, Z3 plus Z3, Z1, Z1, Z2, Z3. Similarly, we can talk about any GNs, GNs as well. And they will have a map from DN to GN. And the thing that turns out is like automorphism of any GN using the similar argument, because this proportion 2 holds for any GN will be isomorphic to automorphism group 1 D. So I just wanted to point out that symmetrized bidisk, the most general version is symmetrized polydisk, and whatever observations we have made here will hold for symmetrized polydisk as well. And one more point to note there is like this process that we have done for corollary 3, which is like bring one of the point to 0 and rotate the other such that it falls under this 0, 1. So what happens is like when you have in GNU, it will be a subset of CN. So this process basically reduce, if you start with, suppose the real dimension is 2 here, when you jump to this process eliminates 2 real dimension, and this rotation eliminates 1 real dimension. So in this case, we are fortunate to get the 4 minus 3, which is just 1 dimension. But if we start with n dimensional GN, then the real dimension is going to be 2n. Sorry, real dimension is going to be 2n. Then the reduction will again be just minus 3, so it will be 2n minus 3. So, for example, if it just checks simple G3, then this process will reduce the set on which you have to check to 6 minus 3, which will be like 3 real dimension. So what happens is, in all these calculations, we have a polynomial in 1 variable, x alone, but there we'll get polynomial in 3 variables. So just to highlight like what happens on symmetric polydisk, even if we go to dimension 3, trying to do this computation even with Mathematica, like it takes quite a lot of time. I'm just reminded when I saw G2 and what happens if automorphism group for GN. I'm reminded of. Any more questions?
Maybe I have a question for Ellen for Guni. So I had I have discussed this with Elanchearan already. Maybe can you go top before the page before that? No, not that one, not that one. Yeah,
This one?
yeah. The
After.
full back.
Okay.
After the symmetric bidisk definition. Yeah. Here,
Okay.
the pullback of the Bergman metric on the G2 coincide with the Bergman metric on unit disk, right? And a polydisk, right?
So what's your question?
Yeah, my question is, in this case, the pullback of the Bergman kernel on the pullback of the Bergman kernel, which coincide with the mm, Bergman kernel on BG2, right?
No. So this
Uh,
expression is different from the Bergman corner on D square. It's just a pullback expression. This is different.
the P star is pullback, right? Pullback of
Yeah, take
Bergman
the
kernel on
pullback. So
G2
it's just a
is same as
coordinate.
the Bergman kernel on the polydisk, right?
No, no.
Oh,
So
okay.
that's a confusion. So this expression is nothing to do with the Bergman corner on this square. So let me just
Oh,
so the term seems a little bit confusing. Yeah, I apologize.
Yeah.
Pull up the
That's why
not
it is.
Bergman. So pull up the not Bergman corner on D square. Pull up the Bergman corner of G2 on D square. That's the meaning. Sorry. So it's confusing. So because those two geometry is totally different. If they are the same, there's nothing to do with this like the work. So because they are already biholomorphic, so
I see.
they're different.
so what do you mean is like by pullback we get Bergman kernel, like by pullback of Bergman kernel on G2 on D2 we have an expression, and by uh, like on D2 itself we have a Bergman metric expression, Bergman kernel expression. They do not coincide.
Yeah, they
Okay.
do not. So there are now two like the functions. One is the
Hmm,
Bergman corner on D square, right?
hmm, hmm.
And another one is we start from the Bergman corner in G2, and we simply just use the coordinate from D square because we know this map. So we simply just take
Yep.
the so two different functions,
Okay.
and they are not the same. If they are the same,
Okay.
that means that their geometries are the same for Bergman space. So that means the Bergman metrics are the same with D square. In that case, it's not interesting. So we already know everything on D square.
I see.
Okay, so in
So
here in generally we can ask a question, right? Suppose we have a like let's say we have a bounded domain D1, D2. We
Yeah.
have a holomorphic function between them, and we have a let's consider we have a Bergman metric respective the domain D1, D2. Is there any condition on the map such that the fullback of a Bergman metric coincide with the pullback of the Bergman kernel coincide with the Bergman kernel on the domain?
I think this is very like a good point to pinching. So for like the relation between the Bergman corner of the Kroc space with the like the Bergman corner of the each. So I believe this is the case. Uh, so so if like the domain and codomain are biholomorphic, then yeah, they must be the same. If the map
They
is
must.
not, yeah, this map is just a surjective, not injective.
Yeah,
So
actually, it seems that this map something proper map, right? As you
yeah,
mentioned, this is a proper map. I just I have searched in this regard in the Google and I haven't get anything about it. I just wanted to ask to you.
So me neither. So I do not. So by holomorphic case, nothing is interesting. So such like a in like a such a like the situation that what if we have just a proper map, proper holomorphic map, then
And
that
also
map
there
affects
is another.
yeah.
We can go with some other some class of covering maps and
Yep. I think that's interesting, like the investigation. I think that can be done further. Yeah, that's interesting question. But I do not know the like the general theme for such a like the case. So what can one tell? But I think this very like a reasonable like the point to investigate, as this one was done. Yeah.
um, uh, I'll just share this once. And uh, actually, in our discussion, it just came up, and we just found this theorem statement. And in fact, uh, so suppose G and D are bounded domains in CN, and such that like we have a proper holomorphic map, and for G onto D of order M. Now GNs are of order n. And the relation between the Bergman kernel on G and D are explicitly mentioned here.
Thanks for letting me know. It's been a while to see this. Right. So this is what one can use. I think exactly this is the behind for driving the expression of the Bergman kernel for G2. Yeah, for sure. So, but it could be extended further. So, for example, also it is known the explicit formula of the Bergman kernel symmetry polydisk. So I think it plays exactly same game. And but still there could be also other the possible the spaces. Let me try to just think. One possible consideration, in my opinion, is so just increase the power of the component. So for G2, so first component is Z1 plus Z2, second component Z1 times Z2, right? So for example, I'm just thinking really just naively. So if we just increase the power reasonably, say C1 square plus C2 square, I'm just giving some example, C1 square plus C2 square and C1 square Z2 square, and just collect just those for example. And we can also generalize those the parameter orders. And the previous, my case was just a case of the order equals or one. Then now the domains are changing. So thereby the Bergman kernel should be changing. Then one can also ask, so then one can try to get the Bergman kernel as just a one the interest the result. So it's a generalization of the symmetry by disk, right? And then one can ask whether or not this phenomenon happens in the same way. Form section curvature is neutral pinch, for example. So this is my the kind of naive the thought from the observation of the one generalization of the Hartog's the triangle that one can just simply just increase the power. Why don't we play the same game, right? So
amazing, yeah. Yeah. It just immediately clicked. It's a mix of Hartog's triangle, generalized Hartog triangle to generalized symmetries. And the idea is now what comes to my mind is with that definition, for example, the coordinates are defined as z1 square plus z2 square, comma, z1 square into z2 square.
Yeah, exactly.
With that in mind, if you are able to compute the, of course, the Bergman kernel expression, you can try to do using this theorem here. And the thing to handle now is the trying to understand the automorphism group of such a thing. If you are lucky enough, and if the automorphism group turns out to be one-dimensional, then computational will be extremely easy, relatively doable.
All right. So any other
I'll stop. I'll just share two things before I end, I think. So one of the point is the statement here. So symmetries, but it's already shown that the Caratha-Reifan metric and the Kobayashi-Radin metric are the same in these two papers. And it turns out that this seems to be the first non-trivial example that is not biholomorphic to not any geometric convex domains. That symmetries by Dix are not convex, and but still these two metrics match the same. So we have in this paper we have not explicitly, or in the presentation we have not explicitly talked about the equivalence of the fourth metric, the Caratha-Reifan, but it's hinted here, and one can refer in these references. This is one. The second thing is we see that the symmetrized by disk turns out to have negatively pinched holomorphic sectional curvature, but the holomorphic bisectional curvature turns out to be positive at some point. And it seems that it is not known whether a non-homogeneous, that is the automorphism group, is not transitive, and it's not product, cannot be written as product of two manifolds. And such a thing exists with a negatively pinched holomorphic sectional curvature and positive holomorphic bisectional curvature at some point. And this result of this paper showed that such an example exists. And these two things I thought I wanted to highlight. Yeah, I think I'll stop here. If you have any questions, you can ask. Otherwise, I'll stop.
If any of you have no questions, then I'd like to just give the extended like the presentation from what Alan today covered. So and this is sort of a concrete like the project idea, and I think this is also good to make the record in public. I don't think nobody can take this like the result from us. So let me share my screen. Uh, Alan, can you just stop to share?
It's already I've stopped sharing. Let me,
All
yeah.
Let me just briefly explain not the so eventually we might go back to that detail later on, but not for today. Let me just make sure what we have discussed for around an hour. If you have complete non-compact, so Kähler manifold, especially we have a Kähler metric, either Bergman metric or the complete Kähler Einstein metric. So, and we assume, or our like the investigation is the complete Bergman metric, not incomplete one. We have this like the one, and we have a like the invariant metrics that we'd like to investigate. So what Ellen today just mentioned is under the condition. So if Holomorphic sectional curvature of this omega is negatively pinched, and this omega was in that like the paper, the case of the Bergman metric on the symmetry by disk, and we just check whether or not this condition is satisfied. Then Uyao just implies this omega is equivalent to the complete Kähler Einstein metric of the negative scalar curvature, satisfy this condition. And it also satisfies with the same constant, so the Kobayashi-Roiden metric. Let me just write this way. So these two are guaranteed from Uyao, like the paper. Is that okay with you? So the condition of the negatively pinched is crucial to construct. So is the construction of the complete Kähler Einstein metric. So behind the basic thing is use Hermander's L2 estimate to guarantee quasi-bounded geometry. So once one get the quasi-bounded geometry, then one can just look at the complex Monge-Ampere equation of complete Kähler-Einstein metric, and this can be solved. This can be solved, and this word is a little bit like the subtle in a sense that this means both elliptic CMA when in Uyao's paper, so it's not like there's no time parameter, and also there's a parabolic one when they handle this condition. So when they handle this condition, they use actually this one. And once they guarantee this guy, then they apply this separately. So it is really subtle to understand the complete Kähler Einstein metric in their like the approach that let me just repeat. So they uses the negatively pinched Holomorphic sectional curvature this condition is used to control the parabolic complex Monge-Ampere equation, and this is usually called by simply just Kähler-Leach flow. And once they have the Kähler-Leach flow to guarantee quasi-bounded geometry, then they just reset up the elliptic Monge-Ampere equation to find the Kähler-Einstein metric satisfying the desired property. So it's a little bit like the tricky for their like the argument. So what one can ask is, what if we lose this condition? So as the symmetry by this case, it was actually just a lucky, truth be told. So when I first initiated that the computation, my very naive intuition was the following. So we have a proper surjective map, and curvature is a local property. And when we look at the D cross D, so Holor's sectional curvature only look at one direction. So that's why Holor's sectional curvature of the D cross D is negatively pinched. Even we rotate arbitrary direction, product like the structure doesn't play the crucial role. And local structure is sort of similar, but mathematically this is illegal to say they behave similar. So that's why I investigated the computation. That's my very the naive thought. And my the co-author Yan just asked me, so are you sure? And I said, well, it might work. So and it worked. It's just that's the reality. So, but it is very not difficult to see that this the assumption fails in many of the other examples. Many of the other examples, this condition is so strong, so one cannot really expect. So with that, the perspective, now you understand what I'm pointing out. So what if this condition fails? Then what can one still say? So let me now go back to one of my another paper. So this one. So let me just show you the main the result. So it's still talking about the equivalence of invariant metrics. However, we'd like to eliminate the curvature negative condition because that's so the strong. So many cases we might not be able to apply. So if you look at this one, I just apply this for the Bergman metric, but this can be extended to many other settings as well, as long as they are invariant Kähler metric. So that we have an n-dimensional non-compact Kähler manifold, and I just assume this metric is complete. This omega B is complete Bergman metric. And now I just assume bounded curvature. So this condition is sort of the necessary condition for the Holor's sectional curvature being negatively pinched. So from Wu Yao's paper, negatively pinched Holor's sectional curvature implies quasi-bounded geometry, and quasi-bounded geometry is far stronger than just a bounded curvature. So this is a necessary condition to get the quasi-bounded geometry. So I just assume bounded curvature, but curvature might be positive. And in general, Holor's sectional curvature of the Bergman metric is from negative infinity to positive 2, and annulus satisfies this condition. And what this the first the statement says is that, so this is the Bergman metric as actually NN form, by the way. So because this is the manifold settings, but in the domain setting, you can just assume this is just a usual the Bergman metric. And this omega B to the n is the wedge power by n times. So this is nothing but the determinant with the local coordinate dz1 wedge to dzn or dz1 bar wedge to dz bar, all of them, NN form. So this is NN form, this is also NN form. So that one can just cancel those the differential form parts in local coordinate. So this just becomes a function. You can just assume this is just a metric, and this is just a determinant if you want. So determinant of the Bergman metric. And if that is just a bounded function, and this fundamental domain is just coming from the automorphism just a group orbit. So we just need to investigate the one point from that orbit because Bergman metric is invariant. So then what we can tell is still there is a complete Kähler-Einstein metric still, such that it is equivalent to the Kähler-Einstein metric. Is that okay with you? So in this the implication, there is no negative curvature condition, but still we can establish the equivalence. So this the result is just I just actually, so even I just mentioned as this first the result, but this is not sort of the illegal in a sense that we didn't really prove this result. I just aside from the just known result in the the form of this setting. So what I really proved in this paper is actually where were we? Let me see. Yeah. This result, this is what I really proved in this the paper, and I use this the implication in the computation of this the paper, so that what I really did is I look at this example. This is a three-dimensional weakly pseudo-convex domain, including the three-dimensional complex hyperbolic space. And in this case, also the Bergman corner is non-explicit, so that one can also initiate to compute the curvature, Holor's sectional curvature. And at this point, we do not really care whether or not Fourier section curvature is negative, and actually it is not. So if one do the computation, one can check. I think I made some remark here. Where it will be. So in this like the class, Fourier section curvature is in general not negative. It could be positive for some of the domains. So let me just show you again. So we just look at this domain. So this is a two, like the parameter, like the family of the three-dimensional weakly pseudo-convex domain. We look at this. And in this case, it is known the explicit formula of the Bergman-Conner, so that one can just apply the same again as Ellen presented today in the case of the three-dimensional, like the case for the Gram-Schmidt procedure, that one can compute the horizontal section curvature, but being negative is false in this example in general. So we just look at the boundedness of the curvature so that this condition can be checked. But this is not easy. So this explicit computation is kind of crazy. And let me just show you again. So this condition is fulfilled for that example. And in that case, this is not hard to check because we know the explicit Bergman-Conner and we know the Bergman metric, and we just need to look at the automorphism orbit. So that's how we establish the equivalence with the Bergman metric and the Kähler-Einstein metric, and also the one compares with the Kobayashi-Roiden metric. Let me show you that part so that we were able to make this like a conclusion. So Kobayashi-Roiden metric is less than or equal to the Bergman metric, and these two are equivalent. So that still some partial result. It's not completely like the equivalence for three invariant metrics, but so yeah, this is still meaningful, like the implication. So let me now go back to note. So in this case, so one like the recent result is when, so all we care is whether or not this guy is finite. So this is equivalently speaking, bounded curvature. They are actually the same condition. Bounded curvature. So, and some ratio condition. Some function should be positive. Some function is bounded. So again, behind, this is the use of the parabolic complex Monge-Amper equation, or simply just Kähler-Lynch flow. And I just adopt like this like the framework in that like the example to establish the like the comparison of three invariant metrics. This is my recent result, and now let's move next like the stage, because this is now done. So next question: what if this condition fails? So now let me just show you again. So if the Fourier section curvature is negative finished, we are happy. So now we have a theorem, so we can just go for it. So what if that fails? Then so one can weaken the condition as a bounded curvature with some additional function to check. So this can be checked because it's just a function condition, so it's kind of okay. And I just use this for the three-dimensional two-parameter family of the weakly pseudo-convex domain to check this condition is indeed meaningful. Is that okay with you up to here? So what if this fails? So this was luckily, me and Ellen actually already checked before. So just to look at this example, counter example, is fat Hartog triangle.
Hello. Yeah, sorry to interrupt. Actually, I
Sorry?
have one more commitment with my supervisor, so I have to leave now. Can you hear me?
Sorry, can you say again?
Sorry to interrupt. I have one more commitment with my supervisor right now.
Okay. Then
Yeah, I would like to leave now.
okay.
Yeah, I can
But I will just make the record
revisit
so
the
that
video.
later on you can take a look
Yeah,
and
yeah, you can share the recorded
Yep.
video. Yeah, or if you want to put, if you are uploading in your website, it's also fine. I
Yep.
can
Yeah,
watch
but I
and
will share something confidential with Ellen today. But yeah, you guys can discuss basically.
yeah. Thanks.
Okay, sounds good.
Thanks. Bye.
Yeah. So for this like the counter example, so but let me just mention what this like the domain is. So this is in C2. This is in C2, and we introduce usually this condition. This is the usual Hartog triangle, but we just introduce gamma here, and let me just call it by Hartog suffix gamma. And the paper, if Ellen remembers this result, so if this gamma is, so if this gamma is 1, this is a usual ordinary Hartog triangle. If this gamma is greater than 1, this is fat Hartog triangle. If this gamma is less than 1, this is thin. So this is what we saw. And if this gamma is a positive integer, which is not equal to 1, so we know the explicit form of the Bergman-Conner from one of the recent paper, Bergman-Conner. And this is a two-dimensional example, so that's why. So when we know the computation of the symmetry by this in everything in detail, so one can just adopt the same the framework. So as far as I understood, so we check two things. Number one, Lorentz sectional curvature of the Bergman metric is at least bounded. So for any gamma. Number two, if I might be wrong, so in that case also let me know. If this condition fails, then this also brings new open new the door to investigate. Number two, that function, ratio function, is not bounded. Unless gamma equals 1. If I remember correctly.
Yes. So these two conditions I would like to verify. It's been some time. So I want to verify once again. Probably I'll do that with Bharati. And then we should confirm once. But this is what I remember.
Yeah. So this the two conditions are crucial in a sense that bounded curvature should be also have the implication regarding invariant metrics. But I'm kind of happy that this ratio function is not bounded any longer. So if that happens, then one need to investigate a new condition to establish the comparison or the equivalence of the invariant matrix. So I'd like to now just assume this is our case. So now we have these two conditions basically. Then how can one come up with how can you establish either the comparison or equivalence? Let me just of this is a question. Is that okay with you? So that now we have a concrete the example that the previous the results does not apply. And in such the scenario, but I still want to assume at least the curvature is bounded, at least. So and truth be told, that might not be really necessary for my the current the attempt that I'd like to share. But this is the situation that I'd like to just think as a most the abstract possible the setting. So and I'd like to share the idea without the record today. But this is
Yes.
today what I'd like to share. So how can we really attack? So I was like the stuck with like the observation, quite like it's been around a year, right? So but now I think um that's one thing I wanna tell. And for today's like the record, I just wanna say one thing to Jocelyn because Jocelyn is interested in like the CR geometry, and I'd like to make all like the participants to take the benefit. So for CR geometry, just one like the piece of the record. So I'm not sure that you look at the Hopf vibration before. I think this is very good to look at in detail. And if you want, you can present. And of course, I can share the note if you request. I think this is very good to learn. So let me explain why this is very, very important for the learning CR geometry. So if you have for example, one like the case is just a S3, but this can be generalized to any odd dimensional sphere. So now you have this like the manifold and you have a natural action, then this is, I explained this to Ellen before, but let me just redo. So this is just a proper subset inside of C2. So the way to define the group action, so define the group action as follows. So now you have a S1 and S3, then we'd like to map this to be S3. How this happens? So we have a e to the I theta, and if you have a Z1 with Z2, then we just simply just define by multiplying each components. That's it. Just take this guy. So this is now the group action. So you can easily check. But one necessary like the observation is Z1 bar plus Z2 bar should be one. So that if you just look at this one as a Z1, let me say prime, Z2 prime, then you need to see whether or not this belongs to S3, not just a C2. So why this condition is satisfied? Because we start from here, and if you just look at Z1 prime bar plus Z2 prime bar, so then Z1 prime just means this guy, so that you can simply just plug in. And now we took the complex conjugate. So because of that, you can see now we should put the negative sign. And these are just scalars. You see, these should be canceled independent of theta. And also the same reason works for Z2 bar. Is that okay with you, what I'm talking about? So that's why they still sit inside of the three-dimensional sphere, so that it makes sense to talk about the natural like surjection to the Poisson space. Because now we have a group action. Jocelyn, does that make sense to you, what I'm talking about? Yeah, I assume you're still listening. So what you can now see is this is P1, complex, like the projective space of dimension 1. So if you have, similarly, you have S2n plus 1, and still you can play the same game. You can define the group action by circle. You can play the exact same game. I just play with just two components, but you can just extend for the n components. Why not? Then you can, by doing the exact same way, you have actually mapped from the odd dimensional sphere to the Poisson space. So what's the definition of this guy? This is complex projective space. So this map is very, very important with two themes. This is Riemannian submersion. And CR structure affects the Kähler structure. These two reasons are important. So CR geometry is weakened than Riemannian geometry, and also is closely related to the Kähler geometry. So when one initiates some like the research work, so it is important to have the very concrete like the example to investigate if you have some like the idea. So here Riemannian submersion means that if you have so let me say condition 1, condition 2, condition 1 means that if you have the Riemannian metric, then we also have the natural like the Riemannian metric as so-called the Fubini metric here as a Riemannian one. So this condition just really means that so T of S2n plus 1, if you just look at the image of this guy so is actually same as just the T Pn as a Riemannian manifold. So I think this is a very bad notation, but what I'd like to say is that tangent like the bundle levels. So these two metrics are actually the same, isomorphic. That's what this means. So Riemannian geometric structure is preserved by this map, Hopf vibration map. This is one key feature. Another important like reason is that metric is preserved. On horizontal distribution of this guy and this one. So they're actually the same. This is the condition of Riemannian submersion. The second condition is the following. So if you look at this like the construction, so we just look at this guy. We look at this guy. What that means is that we ignore S1 direction. We ignore S1 direction. So this S1 direction is generated by so-called the Rib vector field. Rib vector field. So for the dual of the Rib vector field, we call it by the contact one form. Standard contact one form. Let me call it by alpha. So if I just denote this Rib vector field by capital T, then this like the dual just means this equals 1. And this contact condition just means this is a contact condition by the definition. So this condition is fulfilled. So why this matters? The reason is the following. Not the formula, I want to explain the geometric intuition. So we start from the odd dimensional sphere, and we have a circle action. And that circle action creates the infinitesimal, like the direction of the vector fields that would be called by the Rib vector field. And as long as now we have a vector field, then we can take the dual. We can take this co-vector for each like the tangent vectors that would be called by the standard like the contact one form, satisfy this contact form condition. Then now we have a differential one form. Then it is now crucial that you can take the exterior derivative to create the differential two form. And then you can take the push forward by the Hopf vibration map. Then this equals Fubini metric. So that the CR structure of the other dimensional sphere determines the Kähler structure of the complex projective space. And actually, this is just a model case. So conversely, I'd like to say conversely, so if we have so-called the projective manifold is defined as close like a sub-manifold of the complex projective space. And CPN itself is clearly just such an example. If you start from here, so say X with omega, so projective manifold is closed sub-manifold of some projective space with a larger dimension, then there exists circle bundle. P with omega alpha, this is contact one form, such that you can actually do exactly the same like the game. So you have this guy. So it's satisfying push forward of the alpha recovers this Kähler metric. So the CR structure determines the Kähler structure and sort of vice versa. And CPN is such a canonical example, and you have this is everything explicit like the example as and also this is a model case. So that's why in order to study CR geometry, and if you want to link this with either the Riemannian geometry or Kähler geometry, I think it's very, very crucial to understand just like the language in the setting of the simply just S3. S3, then you can play everything very explicit. Then there's just an R behind like the abstraction, and even for the three-dimensional sphere case, there are lots of like the problems that should be solved. Of course, those are quite difficult, but still that's worth to try. So this is in the record I'd like to make. So if any of you have any questions, let me know. Otherwise, I will stop the record and share something confidential. Okay, then let me stop the record here.